All right, in problem 21, in this type of problem, this is really gonna be just applying the second fundamental theorem of calculus, where it's pretty simple. When you have the derivative of integral, you're essentially just undoing the integration. So when you have the natural log of t squared plus 1, you don't have to worry about finding the antiderivative or any of that. All you should have to do is plug in x cubed for t. Get the natural log of x cubed squared plus 1 times, now since one of your endpoints is not simply x, but it's it's a function of x, you just have to then multiply this by the derivative of x cubed. So you multiply this by 3x squared. And you just, let's just simplify it. Let's put the 3x squared in front. So 3x squared times the natural log of x to the 6 plus 1. And your answer will then just be equal to C. All right, 22, we have a slope field. So we want to identify which of these equations matches the slope field. And all a slope field is that, it shows slopes at specific points on a graph. Those slopes are, the dy, dx's, the derivatives of, the derivatives of y with respect to x. So like, there's some techniques you can use to try to, narrow this down. But you could always just plug in numbers and brute force it if you're not sure, like if you're not sure, you're just like worried that you'll make a mistake somewhere. So the idea that one technique in this case, what you can notice is that all along y, the slopes are 0. See, all along y, dy dx is 0, and all along x, the slope is 0 as well. So then it can't be A or B because these would be undefined when y is 0. But the slopes are not undefined when y is 0. The slopes are equal to 0, which is not the same. So it's not going to be A or B. Now we can just look at the sign of the slopes. In this quadrant, the slopes are negative. Whoa. In this quadrant, the slopes are positive. Here the slopes are negative. And here the slopes are positive. So then you can again check, see which of these equations would work. If you have in this case, if you have a positive times a positive, because x and y are both positive, you should get a positive number. But since you have a negative, you would want to have a negative number. So then what would make sense? Let's again just pick a value. You could pick just one. You could just pick 1, 1. So when you find the derivative of 1, 1 in this equation, you would get negative 1. In this equation, you would just get 1. So this is negative, so it can't be this one. But then again, you could check with this one. You can check negative 1, 1, and then see if it matches. And you're going to find out it doesn't match for C, and you're going to find out the answer is D. So again, you could always brute force this, just test points, 1, 1, negative 1, 1, negative 1, negative 1, and then 1, negative 1 if you wanted to just be sure. All right, 23. So it says using the substitution, u equals x plus 1 for the integral of x over the square root of x plus 1 dx is equivalent to, okay, so if we're going to make u x plus 1, what we have here so far is the integral of the square root of u, because that's where your x plus 1 would be. Now, if u is x plus 1, then du would be then dx. So dx would just be there, du would be there. Now we need a way to get this x then, because du doesn't give you that x in its derivative. So if u is equal to x plus 1, that means that u minus 1 is equal to x. So on top here, what we would put is a u minus 1. Instead of just a 1, we would put a u minus 1. And then this integral will be equal to this. Now, we don't have an answer in this form, so let's just rewrite this. Let's rewrite this as u over the square root of u minus 1 over the square root of u du. U over the square root of u. Remember, this is u to the 1. The square root of u is u to the 1/2. So that's basically, this is the same as u to the 1/2. And 1 over the square root of u. So this is the same as u to the negative 1/2. The square root is in the denominator. So minus u to the negative 1/2 du. And then your answer should then be C. All right, 24, we're given that f is equal to this function, where we got 2x squared plus 14x minus 16 over x squared minus 9x plus 8. So it's asking for what values of x does f have a removable discontinuity. Okay, so let's factor this out and let's see what cancels. So we could rewrite f of x as, we can factor out 2 on the top, 2x squared plus 7x minus 8 over the bottom. You can factor in x minus 8 times x minus 1. You can further factor the top into x plus 8 times x minus 1 over x minus 8 times x minus 1. So you can cancel out the x minus 1 groups. You can't cancel out the x plus 8 over the x minus 8. So since you can cancel out this group, it has a removable discontinuity for this 0. So it has a removable discontinuity for x equals 1. Not for 8 or not negative 8. So then the answer would simply be A. And one way I kind of tell my students to remember, when is it a removable discontinuity? It's like it's like literally removing it from the equation, and you're removing that group. So remember that, like when you remove the group, it's going to be a removable discontinuity. That means there's going to basically be a hole at that point on the graph. There's not going to be an asymptote. There's going to be a hole in the graph. 25. Which of the following is the solution to the differential equation? Y double prime equals 4y minus 4 equals 4 y double prime minus 4y equals 0. So again, this is an example where you could just plug in the possible answers and check to see what works. Differential equations, there are just techniques to solve them. There aren't really formulas. Now on your AP exam, they usually won't make it tedious. So I just advise just to plug in the answers and see what works. All right, so y double prime minus 4y equals 0. So if y is equal to e to the 2x, y prime will equal 2 e to the 2x, and then y double prime will equal to 4e to the 2x. Okay, so checking if it works in here, that means we'll have 4e to the 2x, because that's our y double prime, minus 4y, so minus 4 times this, so minus 4e to the 2x is equal to 0. And right away, that's our answer. We get that those cancel and you get 0, 0. So your answer is A. You're going to go further and verify the other ones, and you'll see that those won't work. It's literally as simple as that. So we got lucky on that one. All right, 26. All right, 26, we got this table that shows values of the continuous function f at some values of x. And it says that f has exactly 2 critical points on the open interval 10 to 14, which of the following must be true. Okay, so when it comes to problems like these, I advise just drawing a sketch of the graph to get a clear sense of what's going on. Doesn't have to be a good sketch. I'm not going to draw a good sketch here, but just sketch to see what would make sense. So 10, 11, 12, 13, 14. So 10, 11, we'll say 12. We have a value at 5. So 10, 5, 11, 2, 12, 3, 13, 6, 14, 5. And it says it's continuous, so these points have to connect somehow. Now, here's the thing. We don't know how they connect. We don't know if they're going to go up and then down, or down, then up. But we're given some information that it has 2 critical points on this interval, and we're told it's continuous. So we know it's all going to connect. And since it has 2 critical points, you can see that the graph from here, in order for the graph to get to here, it has to decrease. It has to go downward. I'm not saying it goes downward like that, but it has to go downward. Maybe it goes down like this and goes up. But here's the thing. Maybe it goes down like this and goes up like that. But in order to get from here to here, it has to then go up. So it changes direction somewhere. It changes direction. So we know there's a critical value somewhere over here. Because it has it, maybe it does something like this. Maybe it goes maybe it changes direction there. But it has to change direction. So there has to be some, again, a critical value somewhere there. Because it says 2 critical points. So maybe there's a tangent line there, horizontal tangent line there. And likewise, to get to here, it's going to go up. But then to get from here to here, it has to go downward somewhere. Maybe it goes straight down like that. Maybe it does this. Who knows? But it has to go downward at some point. So our other critical value is going to be in that region over there. So let's just go through each one. So f of x is greater than 0 for all x in 10 to 14. Even though all of these are greater than 0, you could have your graph could hypothetically go like this, and that'll be fine. So it doesn't have to be this. It doesn't have to be greater than 0. You could dip below. F prime of x exists for all x in the open interval. Not necessarily, because you could have a sharp point. You could have maybe something like this. Just because it's continuous doesn't mean the derivative is defined everywhere. A critical value doesn't have to occur where the derivative is 0. The derivative actually doesn't have to technically be defined at a critical point. So it doesn't have to. So it's not necessarily B, because there could be, again, sharp points on this open interval. The first derivative is negative for all x. Definitely not, because it has to, again, go up somewhere. It's negative some parts, but it can't be negative for all of them, because it goes up. It increases. So just by process of elimination, the answer is going to be D, and it's also D. We can say it's true because, again, the derivative at 12 is not going to be 0, because it has, again, it's increasing.